I welcome you to today's lesson on vector spaces. This lesson is taken from your second year BSc portion on the course number 2 Algebra. Vector spaces play an important role in many branches of mathematics like linear algebra, numerical analysis, etc. The vector spaces we study today are in fact called general vector spaces. In future, in your higher studies, you will be studying topological vector spaces. There is close relation from general vector spaces to topological vector spaces. The topological vector spaces help us study quantum mechanics. Today, let us enter the topic vector spaces. First, we start with the definition of a vector space. We take a non-empty set V. We define when this set V is a vector space or a field F. You may recall the definition of a field F. F is said to be a field if it is an abelian group under an addition plus and its non-zero elements form a group under multiplication and it satisfies certain distribution laws. You may also recall that the set of real numbers forms a field, the set of complex numbers forms a field, and the set of rational numbers also forms a field. Now, we define when a non-empty set F or a field F is a vector space. We want two operations plus and dot defined as follows. The first one is that V plus should be an abelian group, means plus should be a binary operation on V, plus should be associative on V, there should be additive identity with respect to plus on V, and for every element u in V there should be additive inverse and plus should be commutative on V. Then we say V plus is an abelian group, means plus is closed on V, plus is associative, plus E has identity element, plus has additive identity, and plus is commutative. Then we say V plus is an abelian group or a commutative group, and there should be scalar multiplication dot defined on F cross V as follows. This dot is which we call scalar multiplication should be a function from F cross V into V, taking ordered pair A comma U into A dot U. We denote A dot U by A into U. If there is no symbol between A into U, we mean that there is scalar multiplication dot between them. A is coming from field F and U is coming from set V, and this dot scalar multiplication should be satisfying the following properties. It should be distributive over the addition in V, that is A into U plus V must be AU plus AV. This is scalar, A into something is scalar multiplication, U plus V is coming from V, so A into is this is scalar multiplication and this plus is plus in V, and then A plus B into U should be equal to AU plus BU. Here A and B are coming from field and therefore this plus is the plus in the field, and A plus B is an element in F, and the elements in F are called scalars. The scalar is multiplied by U from V, so this is scalar multiplication. It should be equal to AU plus BU, means the scalar multiplication should be distributive or the addition in the field, and then AB into U should be A into BU. Here A and B are again coming from F, and this is A into B is the product of A and B in the field, and this scalar is multiplied by U, therefore this is scalar multiplication. And again B into U is a vector in V, and scalar B is multiplying U, this is scalar multiplication, and again this vector is multiplied by another scalar, this is scalar multiplication, means the multiplication in the field must be compatible with scalar multiplication. That is what this property 9 says. The final property says 1 into U should be U for all elements U in V, and if we have a non-empty set V with plus and dot satisfying all these 10 properties, we say V plus dot is a vector space over the field F. Let us look at some examples of vector spaces. Example is R plus dot is a vector space over R. Here R is the field of real numbers, or simply the set of real numbers. We know that the set of real numbers is an abelian group under addition. Therefore, R plus is an abelian group, and we may recall that if we add two real numbers we get a real number, and addition of real numbers is associative, and 0 is the additive identity, and for every real number x, minus x is its additive inverse, and we know that if we take any two real numbers x and y, x plus y is same as y plus x. Therefore, R plus is an abelian group, and this dot is the usual multiplication of real numbers. We can see that R plus dot satisfies all the 10 properties that are defined in the definition of vector space. Therefore, R plus dot becomes a vector space or field R. Here this R plays the role of F in the definition of vector space. Another example is C over R, C plus dot over R is a vector space. C is the set of complex numbers. We know that the complex numbers form an abelian group under the usual addition, and under the usual multiplication of complex numbers by real numbers, we can see that C plus dot satisfies all the 10 conditions in the definition of vector space where field is taken as R. Therefore, the set of complex numbers form a vector space over R. We can also see that C plus dot is a vector space over C itself. In place of F, we can take this field of complex numbers in the definition of C in the definition of vector space, and we can see that the complex numbers satisfy under the usual multiplication and the usual addition of complex numbers. We can see that C plus dot satisfies all the 10 conditions in the definition of a vector space. Therefore, C plus dot becomes a vector space or the set of complex numbers, and R power n plus dot over R. If you take the Cartesian product of R with itself n times, we get R power n, R cross R taken n times, and this plus is the component wise addition, and this dot is multiplication of an n-tuple by real numbers. If you define the addition on Rn and scalar multiplication on Rn like this, you can see that R power n plus dot becomes a vector space or R. By the way, the elements in the vector space are called vectors, whether they are n-tuples or n-dimensional vectors, whatever they are, the elements in the vector space are called broadly vectors. Well, let us look at some figurative examples of vector spaces. Let us look at some more examples. Let us consider the xy plane. The usual xy plane is R2, it is R cross R. This is x axis, this is y axis. You look at the points P, Q, R, S in the xy plane. Every point in the xy plane has an ordered pair as its coordinates x comma y, and if you take the position vector of this P, you have OP as a 2-dimensional vector xi bar plus yj bar, and therefore there is a 1-to-1 correspondence between the points in the xy plane and the 2-dimensional vectors, and you can see that this R2 forms a vector space with the usual addition of 2-dimensional vectors. If you take ordered pairs x1 comma y1 and x2 comma y2, you can define their sum as x1 plus x2 y1 plus y2, and if you take the ordered pair x1 comma y1, you can multiply it by a real number a, as a into x1 y1 is ax1 comma a y1. So you can see that under these plus and dot, R2 becomes a vector space. The next example is R3. You look at the points in the 3-dimensional space x, y, z. These are the coordinate axes x, y, z. You look at all the points in the space, they are like P, Q, R, S, T, U. They have individually order triples as their coordinates, some x1 y1 z1, x2 y2 z2 and so on. You can define some of these vectors p and q as x1 plus x2, y1 plus y2 and z1 plus z2, and you can define the scalar multiplication as a into x1 y1 z1 is ax1 comma a1 y1 comma az1, and under these addition and scalar multiplication you can see that R3 plus dot is a vector space over R. Here the points in the space are in one-to-one correspondence with their position vectors. The position vector of P will be something like x1 I bar plus y1 j bar plus z1 k bar. Well, so in general Rn plus dot is a vector space over real numbers, and if you look at the Cartesian product of C taken n times, that is C cross C cross C taken C n times, under the usual addition and scalar multiplication you can see that Cn plus C Cn plus dot is a vector space over the field of complex numbers. Here addition is component wise addition and scalar multiplication is component wise, and here now we can talk about something which is not a vector space. R plus dot over C is not a vector space. I am taking the real numbers with the usual addition and the multiplication, the scalar multiplication and the usual scalar multiplication. Here my field is the set of complex numbers. If you multiply a real number by scalar complex number, the product will sometime become complex number. So for example I2 into 3 is I6, and I2 is a complex number, 3 is a real number, but the scalar multiple I2 into 3 is I6 is not a real number, therefore this is not a vector space. Well, whenever we have a vector space, we denote it by this triple V plus dot, say it is a vector space or a field F, and if W is a subset of V, we may ask whether this W is also a vector space. You may recall that if you have a group G, if some F is contained in G, and if this G is a group under a binary operation plus, we are asking whether its subset F is also a group with respect to the plus here. If F is a group with respect to plus, then we say F is a subgroup of G. Similarly, here we may ask a subset W whether it is a subspace with respect to the plus and dot defined on V. If it is so, we say that this W is a vector subspace over the same field F. In R2, any line passing through the origin is a vector subspace of the vector space R2. We know that R2 plus dot is a vector space over R, and you take any line y equal to mx passing through the origin, you can see that the points on that line form a vector space with respect to the addition and scalar multiplication defined on R2 plus dot. Therefore, any line passing through the origin forms a vector subspace of the vector space R2, and if you look at this line M, which is not passing through the origin, you can see that it does not have 0 element on that. No point on the line M has position vector as 0 vector. Therefore, this line M is not a vector subspace of the whole space R2. Say we have two planes and see that their intersection is a line, means we have two intersecting planes. If this line passes through the origin, then we can say that these planes are vector spaces and this line is also a vector space. Say we have a vector space V and vector subspaces Wi. in V. The question is, what can we say about the intersection of all these vector spaces? Well, we can show that the intersection of all these vector spaces also becomes a vector space with the same addition and scalar multiplication defined on V. Before going to this, we should talk about a criterion of a vector subspace. So, we have V plus dot is a vector space and W contained in V is a vector subspace. Means if x1 x2 belong to W, we have x1 plus x2 is in W, because W, I am assuming that W is a subspace of V, therefore, and these are coming from W, and therefore their sum should be in W, and also alpha times x1 should be in W whenever alpha is from the field. I am assuming V is a vector space over field F. If alpha is coming from the field, alpha into x1, this is a vector, alpha into x1 becomes a vector in W, and because I am assuming W is a vector space, alpha x1 is also in W. So, whenever W is a vector subspace of V and x1 x2 are coming from W and alpha is coming from F, then we have that x1 plus x2 is in W and alpha x1 is in W. We have a determining criterion for a vector space as follows. I am assuming V plus dot is a vector space over F. So, and also I also assume that W is a subset of V. We have the following theorem. W is a vector subspace or a linear subspace if and only if alpha x plus beta y belongs to W for all alpha beta coming from F and x comma y coming from W. This is a determining criterion for a vector subspace. Here we are assuming W is a subset of a vector space V on which we have vector addition and scalar multiplication, and F is the underlying field. W is a vector subspace in V if and only if this condition is satisfied. Let us assume that W is a vector space, then we can obtain this. Here x and y are coming from W, alpha and beta are coming from F, and alpha into x is scalar multiple of x, and W is a vector subspace, therefore alpha x is in W. Similarly, beta is a scalar and y is a vector, and beta into y is a scalar multiple of y, and W is a subspace, therefore beta y must be in W, and therefore, and these are now vectors, alpha x and beta y are vectors in W, and W is a vector space and their sum should also be in W, means alpha x plus beta y belongs to W. So, this implies this. Conversely, let us assume this, then we can obtain this. Well, if you take alpha equal to 1 and beta equal to 1, where 1 is the multiplicative identity, 1 into x becomes x, 1 into y becomes y, and for x comma y belonging to W, 1 into x plus 1 into y is x plus y, that is in W. Means if you take two vectors in W, their sum is also in W, and if you take beta equal to 0, 0 into y becomes 0, that is the 0 in W, and alpha into x plus 0 becomes alpha x, and means for alpha coming from the scalars and x coming from the vector space and x coming from W, alpha and x is also in W, means W is closed under vector addition and scalar multiplication. Therefore, you can see that W also becomes a vector space in V, therefore W becomes a vector space. Say we have any collection of vector subspaces of a vector space, say over a field F. The question is, what about the intersection of these vector subspaces? Is it also a vector space? The answer is yes. Let us look at that. So, we have lambdas are varying over an index set capital lambda, and I am assuming that V is a vector space, and I am collecting various vector subspaces. W lambdas are vector subspaces. To show that, I want to show that intersection of W lambdas where lambda varies over lambda is also a vector space. To obtain this, let us check this condition. Let us collect x comma y coming from this intersection, and alpha comma beta coming from the field. X comma y are coming from this intersection means x comma y belong to each of these sets. X comma y belong to each of these vector spaces, therefore x comma y belong to this, and W lambda is a vector space, therefore alpha x plus beta y belongs to W lambda, and this happens for each and every lambda, therefore alpha x plus beta y belongs to this intersection. Thus this intersection becomes a vector space of a vector subspace of W. Once this happens for intersection, we can ask what happens to union. Means if you have two vector spaces W1 W2, is their union also a vector space? Is their union also a vector subspace of V? Means I am assuming that W1 W2 are vector subspaces of V under the same plus and dot or the same field. The question is, what happens to their union? Is it also a vector space? The answer is no. Let us look at an example. You have this situation. In R2, you take any two lines passing through the origin. This is x axis, this is y axis. You take any two lines passing through the origin, each of these is a vector subspace of R2. Now if you take any lines, any 2 points on these two vector subspaces, and if you join them, this intermediate point is not a member of their union, right. This is some point P, this is some point Q, this line L1, this line L2 are vector subspaces of R2, and I am collecting P from this vector subspace and point Q from this vector space, and their linear combination, this point, if you take an intermediate point on the line segment joint PQ, that becomes a linear combination of P and Q, but that is not a part of W1 union W2, means W1 union W2 is not closed under vector addition, therefore it is not a vector subspace. Well, the question is, when does this union become a vector subspace? The answer is the following: W1 union W2 is a vector subspace if and only if W1 is contained in W2 or W2 is contained in W1. Let us prove this. You can call this a theorem. We will show that W1 union W2 is a vector subspace if and only if either of these contained in the other, means W1 is contained in W2 or W2 is contained in W1. This part is easy, if part. If W1 is contained in W2, then their union is this W2 and W2 is a vector space. I am assuming that W1, W2 are vector subspaces. W1, W2 are vector subspaces. So if W1 is contained in W2, their union becomes the larger one W2, and W2 is assumed to be a vector subspace, therefore their union is also a vector subspace. And similarly, you can see that in this situation W2 contained in W1, the union becomes W1 and W1 is assumed to be a vector subspace, therefore union also becomes a vector subspace. Now coming to the only if part, let us assume that W1 union W2 is a vector subspace, and if W1 is contained in W2, it is okay, we are safe. Say W1 is not contained in W2, means there exists an element in there exists an element x 1 belong x1 belong or simply x belonging to W1 which is not in W2. Now, let us collect any y belonging to W2. We will try to show that this y belongs to W1. If we can do that, we will obtain that W2 is contained in W1 and we obtain this part. Therefore, this whole thing holds good. In this only if part, we assume that W1 union W2 is a vector subspace, and if W1 is contained in W2, it is fine. Otherwise, we obtain an x in W1 which is not in W2, and we will show that every y in W2 is also in W1. This brings us that W2 is contained in W1, and hence this becomes an if and only if condition. Thus, a union of two vector subspaces is also a vector subspace if one of these vector subspaces is contained in the other. In this lesson, we have defined when a non-empty set V becomes a vector space over a field F. We looked at various examples and we looked at some geometric figures also as examples and some as non-examples, and then we discussed intersection of vector subspaces and saw that vector subspaces intersect in a vector space, and we looked at some examples of vector subspaces whose union is not a vector space, and we obtained a criterion for union of two vector subspaces to become a vector subspace.